Okay, we've been talking about gases here, and we talked about a bunch of gas laws. We talked about some important units as well in terms of gases. Remember that 1 atmosphere is equal to 760 torr, which is equal to 760 millimeters of mercury. And we saw several different units, but those are sort of the big three units that we kind of come across the most: atmospheres, torr, millimeters of mercury. And again, that 760 number is really important, as that is obviously the way that we convert between them. If you have atmospheres, and again, want to end up at either torr or millimeters of mercury, you need to multiply by the 760. And obviously, opposite there, if you have millimeters of mercury and you want to end up at atmospheres, you're going to divide by the 760 there. Remember, it is a 1-to-1 relationship between those two units. So if you need to convert between them, really, it's just kind of changing the units. It will come out to obviously to be the same number. We talked about a number of different sort of gas laws. We had our friend Boyle there that looked at the pressure volume relationship, holding temperature constant. And remember that what we saw here is pretty much as one went up, the other went down. So as the pressure went up, the volume went down, and vice versa. As the pressure goes down, the volume goes up. Again, as we talked about, it's pretty much the volume there. At a much smaller volume, there's going to be more collisions as the gas molecules are flying around, and that's going to cause an increase in pressure. Again, a larger volume going to give everybody a little bit more room to sort of fly around. Going to cause less collisions, going to see a decrease in the pressure. We saw Charles' law as well. And Charles' law, which is our V1 T1 equals V2 T2. This is at constant pressure. And what we saw here is as the volume goes up, so does the temperature. And as the volume goes down, so does the temperature here. The relationship that we saw is pretty much that is how the pressure is able to remain sort of constant, is the volume that sort of adjusts with the temperature. So as we increase the temperature, we do expect our gas molecules to fly around a lot faster, which means we would expect more collisions to occur. What allows it to not sort of occur that way is that the volume will adjust accordingly. So it gives everybody a little bit more room to fly around in. So even though they're flying around faster, the number of collisions remains relatively constant. And that's what keeps our pressure constant, both with the increase in temperature and also decrease in temperature. If we decrease temperature, the opposite is sort of true. As we sort of slow down everybody, they're flying around slower. We would expect less collisions to occur. So that volume sort of adjusts to a smaller volume. So even though they're moving slower, it's going to keep that rate of collision sort of constant and also keep that pressure constant. This is where we also saw one really important thing for pretty much all gas laws, which is the temperature value. And as we talked about, pretty much the temperature always needs to be in Kelvin. So that's a temperature in Celsius plus a 273 to get it to Kelvin. If it is a gas law, as we talked about, you do need to get it into Kelvin. Even again, if they sort of give you the numbers in Celsius and they want the answer in Celsius, you do have to convert it to Kelvin to put it into the gas law and then convert it out of Celsius at the end of it. We also talked about Guy-Lussac's law there. And that's our P1 T1 equals P2 T2 relationship. This is at constant volume. So in this case, as we talked about, because we have that constant volume, like in a rigid sort of container, when we do see that increase in temperature, we will see a corresponding increase in pressure, again, because those gas molecules are moving a lot faster. And unlike in the Charles case there, we're not going to get any adjustment with the volume. So the volume is going to be fixed. So that is definitely going to increase the rate of collisions. And the result of that is we will see an increase in pressure. And opposite as well here, as we lower the temperature, we will start to see the pressure to decrease as well. Again, for the same reasoning. If we lower the temperature, going to be moving around slower, the volume's not going to move, so the rate of collision is going to decrease, and thus the pressure as well. We also saw our friend Avogadro, which is our V1 N1 is equal to V2 N2. And this was at two different sort of conditions, constant pressure and temperature. And what we talked about here was a couple of things. The relationship here is basically as the moles increase, so does the volume of the gas that's happening there, sort of proportional to each other. What we also talked about was the idea that in a sort of Avogadro situation where we do have pressure and temperature being held constant, we could also use that for a little bit of stoichiometry relationship, as we talked about. And again, without having to use a gas law. And if all these guys were gases, instead of doing a mole to mole relationship like we can do in a basic stoichiometry problem, we could do a volume to volume relationship if all these guys are gases. And again, we're at constant pressure and temperature. So it allows you to make you do a little bit of stoichiometry, as we talked about. I think we did a little example there as well, where you might not have to use a gas law. Putting all these guys together gives us our PV is equal to nRT, which is our ideal gas law. Remember that this is the most restrictive. Pressure has to be in atmospheres. Volume needs to be in liters. N should be in moles. And T should be in Kelvin, just like, again, all the other T's that we see in any gas law. And that is because R is 0.08206 liters, atmosphere, Kelvin, a mole. And that, again, is a constant that you always have available to you. Once again, not usually given to you in the problem, but just assume that obviously you have that available. Also, you do need to know this number, and here the units that go with it will give you the units that everybody else needs to be in when we use this. An ideal gas here is sort of a one, or the ideal gas law is sort of a one sort of situation, one pressure, one temperature. You know, we can kind of use it for that. We also talked about STP, which is standard temperature and pressure. And that is basically a temperature of 273 Kelvin and a pressure of 1 atmosphere in that particular case. And we also saw a really relationship that you can use at under STP conditions, which can allow you not to maybe have to use the ideal gas law, which means at STP. And remember, it has to be at STP to use this conversion. 1 mole of any gas will equal 22.414. So as we talked about last time, if it is at STP, you could kind of use the conversion maybe and sort of bypass the ideal gas law. If you're not sure you should use it, you could always use the ideal gas law, as we talked about, under any conditions, STP conditions, non-STP conditions, and all those type of things. Lastly, here in our journey through all these gas laws here was the combined gas law, which is our P1 V1 over T1 equals P2 V2 over T2. Once again, here pressure and volume can be any unit that you like, as long as they are the same. Our temperature here, again, on both sides does need to be in Kelvin. If you remember, we sort of finished with this one, and I said that if you were sort of to invest in remembering all these equations, which you do need to know, the ideal gas law, and really this version of the combined gas law are really good ones to remember. Once again, just a reminder that if you remember sort of this combined gas law, and anything that's held constant or not given to you, just scratch out. Again, if you didn't have moles or temperature or they're constant, you scratch them out. And again, there's for Boyle's law. Again, if you didn't have a pressure given to you or moles is held constant, you just scratch those out. And once again, there's Charles' law. So this is a really good one. You basically can scratch out anything that's held constant that's not given to you, and you probably find the gas law that you need. Any questions on any of that stuff there that we talked about last time? All right, so I think we left off right around here with this example. So why don't you give it a go? Consider a sample of oxygen gas at 27 degrees Celsius, volume of 9.55 liters, and a pressure of 297. It's changed to 8.25 and heated to 125. What is the new volume? Okay, let's take a look. So once again, as we talked about last time, also a really good idea when you're dealing with sort of gas law problems is to pull out the information and just label them. So obviously here we have a temperature that is 27 degrees Celsius. We have a volume that is 9.55 liters, and we have a pressure that is 2.97 atmospheres. The pressure is changed to 8.25. And we have another temperature here of 125 degrees Celsius, and we are looking for a volume. So again, obviously we can see here, we got multiple P's and V's and T's, and you could probably see the combined gas law in there. And again, that's a really good way to approach these problems. It will also kind of point you sortfully in the right direction as to what you need to use to solve. In terms of units, when we look at this, and we could call the first set here, guys, 1s and 2s. We have atmospheres on both our pressures, which means we're okay there. But we do have Celsius, obviously, here with our temperature, which is very common. So we do have to do that conversion. So we're going to add a 273 to each of those. And when we do that there, we're going to get a 398 Kelvin. And a 27 and a 273. That's not it. 20 plus 273. I'm gonna go to the left here, 300 Kelvin. Now we got everybody in the correct units here. We could take our combined gas law. And in this case, we're looking to isolate our V2. So we do need to multiply the T2 to the other side. We also need to divide by the P2 to the other side. And again, as we talked about, they essentially will end up, if you want to kind of do it quickly, they'll end up in the opposite locations of basically where they started. So that will get us T2 P1 V1 divided by P2 T1 is equal to V2. Reminder that what you are solving for needs to be up on top. Otherwise, if it's on the bottom, you're doing 1 over what you're looking for. So you got to make sure everybody gets to the right side. Put in the right numbers here. Our T2, 398. Our P1 in this case, 297. Our V1, 9.55 liters. Divided by our P2, which is 8.25 atmospheres. And our T1, which is 300 Kelvin. In terms of units, kelvins will cancel, atmospheres will cancel. That's going to leave us liters as the only unit left in this case. 398 times 2.97 times our 9.55 divided by 8.25 and divided by 300. Going to give us something like 4.56 liters here. Any questions on that calculation there? Yeah. Yeah, so really we would go with 3 sig figs probably on all this. You may be looking at this one like it's 300 with nothing written, but the original temperature value is a whole number, so we would probably go with leaving this still at 3 sig figs when we kind of convert it to a whole number, because we would go technically to like 300 point because we want to take it to a whole number when we do that temperature conversion. So basically we're looking pretty much at 3s all the way across on everybody. So 3 is probably where it should end up. Yeah. So it's a little kind of tricky in a sense with the temperature, but for example, again, if that temperature was a whole number, you would take it to whole number. Even if that whole number ended up like zeros like it did here, you would kind of take all the numbers there as for sig figs. Other questions? So I would say, again, this is the one that gives people a little bit of difficulty, and it's the rearranging part. So make sure, again, you just know how to properly rearrange that. Any questions on the combined gas law? Okay, then we're going to talk about stoichiometry involving gases. And when we do stoichiometry involving gases, it really is the same sort of 4 steps that we use for basic stoichiometry problems, or really any stoichiometry problems. We want to make sure always in stoichiometry that we start with a balanced equation. Remember that nothing works right if you don't have a balanced equation. We want to convert to moles. And again, same idea, whatever they gave us, we want to get them into moles. We also want to determine as well, is it a limiting reagent problem, right? Because it could be, even in gas stoichiometry, we could still have a limiting reagent problem. And the way that we know it's a limiting reagent problem is what is given to us that we know it's a limiting reagent problem. Yeah, we got enough information really to get the moles of each reactant, right? So that's the key, right? However we get there, we have enough information given to us to know the moles of each one. And if that's the case, then it is a limiting reagent sort of component, which we do have to take that into account. If it's not, and it's just like a basic problem, you're just given maybe one piece of information, then you could roll without doing the limiting reagent part. We then want to go to the mole to mole relationship from the balanced equation. And lastly, we want to convert our moles into some other unit. So pretty much, even though these involve gases, they're pretty much just really stoichiometry problems. The main difference is, honestly, you're going to use the ideal gas law in most cases, I would say, at some point. So at some point, you're going to use PV is equal to nRT in the solving of these problems. And there's two really common places where you might use it. You might use it up front. So instead of normally going from grams to moles using the molar mass, we may use the ideal gas law up front and solve for N, which would be PV over RT. So maybe we are going to use the ideal gas law up front, solve for N. At that point, it'll probably be very similar to a normal stoichiometry problem, and you'll continue on with your mole to mole relationship. The other more common place that you probably will use it is at the end. You'll use your ideal gas law here at the end, really to solve for a couple things. In a lot of cases, most likely going to be volume is very common at the end. So I would say those are probably the two common places in sort of the stoichiometry movement that you may use your ideal gas law. In theory, you could technically use it at both places, but in a lot of cases, usually it'll just be one spot, either the beginning sort of or at the end. And I would say probably most of the time at the end is sort of where you probably use it. But again, you could use it earlier on. Any questions on any of those steps there? Okay, so let's take a look at one here together, through this one on here, and we'll go through these steps just again to show you sort of how it works and how it's very similar to problems that we've done previously. In this case, we want to know what is the volume of CO2, which is over here. That is produced at 37 degrees Celsius and a pressure of 1 atmosphere. And we're going to start with 5.60 grams here of our glucose in this case. And we're looking for a volume. So if we just look at sort of the CO2 information, we could kind of see the ideal gas law shaping up there. And if we write that out there for our CO2 PV equals nRT, we are looking for a volume. They gave us a pressure. They gave us a temperature. And remember, we always have R. So really in this case, what we are missing to allow us to get to the answer is the moles of CO2. And that is pretty much our missing component here. And that is going to come about from really stoichiometry. So if we think about, this is pretty much all the information for my CO2 and my gas. The only piece of information I got left is over here at glucose. So this is where stoichiometry is going to come into play. We could go from glucose to CO2 by really just doing a basic stoichiometry problem to start with. So the first thing we want to do is have an equation and make sure it's balanced, which it is in this case. The second thing we want to do is convert what they gave us to moles. So once again, everything in the box here is pretty much for the gas law at the end of the calculation. That means that this is the only guy that we have to work with at this point. In order to go from grams to moles, we do need the molar mass of our glucose. So that's going to be 6 times our 12.01 plus our 12 times our 1.008 for our hydrogens, and plus 6 times our 16 for our oxygens here. And that's going to give us a molar mass here. About 180.2 grams per mole. Remember, when we calculate our molar mass, it is based just on the formula. And again, usually 4 significant figures is where we take it to. We're going to use that as our conversion factor here. So that's going to be 5.60 grams of C6H12O6. Remember here, we want units to cancel. So we got to go opposite in dimensional analysis. So 180.2 grams per mole of C6H12O6. The grams are going to cancel. And if we get our answer right about now, which you don't necessarily have to get an answer, but if you did, oops, helps to punch it in, right? That helps too. You can go with 0.03107. And again, I'm going to take it to an extra digit because I'm not really done with my calculation here. And that's going to get me to our glucose. But remember, we need moles of CO2. So that is where we're going to use our mole to mole relationship from the equation, which is really our third step in this process. So our third step from the equation, we can see 1 mole of C6H12O6 gives us 6 moles of CO2. So that is going to allow us to go from the glucose to the CO2, which is what we want. So we will continue on with that number from above. We go with 0.031077 moles of C6H12O6 using our mole to mole relationship from the equation. For every 1 mole of C6H12O6, we get 6 moles of CO2. And at this point, we will times that by 6. And we could kind of clean it up at this point to maybe 0.186 moles of CO2. So up until this point, it's really just a basic stoichiometry problem like we've done before. We've taken our grams, we converted our grams to moles. We use the mole to mole relationship to figure out the moles of CO2, which is really what we're interested in. At this point, instead of using the molar mass for CO2 to figure out how many grams that would be, here we're looking for the volume of the gas at a specific pressure and temperature. So now we could take that number and go into the ideal gas law to do that. So kind of a whole stoichiometry problem, finishing though with really an ideal gas problem here. So let's take a look at it here. I'm going to pull the numbers over. So we got PV equals nRT. We just solved for 0.186 moles. And we have a temperature of 37 and a pressure of 1 atmosphere. And obviously here we always have R, which is given to us. So now we can rearrange our ideal gas law and solve for volume. We do have to do a couple of conversions, actually just one. We just need to add 273 here to our 37 to convert it into the proper units. It's going to be 310 Kelvin. Now we're good to go. We're going to take our 0.186 moles, our gas constant, which you always have, all divided by our pressure of 1 atmosphere in this case. Once again, the atmospheres on top will cancel, the Kelvin will cancel, the moles will cancel. That's going to leave us liters, which is good because we are solving for a volume. So 0.186 times 0.08206 times 310 hit equals divided by 1. Going to give us a 4.73 liters here of CO2 would be produced in this case. And by the way, that would be like your theoretical yield. Any questions on any of those steps there? Yeah. Yeah, I personally use 0.08206. I think a lot of people here will use that number, but some books nowadays will round to like 0.0821. So I'm good with if you use either one. But a lot of people will use that kind of 0.08206 number. But a lot of books now will use that 21. Yeah. Other questions? And again, in terms of sig figs here, basically 3 all around. Again, with that 310, again, we hit a 0 at the end, but it was a whole number when we converted it. So we're going to kind of count that 0 at the end as being significant in terms of the calculation. Any questions on any of those steps? So here, really the same basic 4 steps, kind of finishing with an ideal gas law. Why don't you try one here? So consider this reaction. What volume hydrogen gas at 27 degrees Celsius and 1.82 atm are required to react with 5.65 grams of phosphorus? I believe a couple of numbers will be helpful. Phosphorus 3097 and hydrogen 1.008. All right, take a few minutes, see what you come up with. Again, follow those steps, see what you come up. Okay, let's take a look. So in this case, we're looking for the volume of hydrogen gas. We have a temperature of 27 degrees Celsius. We have a pressure 1.25 atmospheres, and we have basically 5.65 grams of that guy. So once again, we could kind of focus in here and see we're kind of shaping up into our ideal gas law, as we always have R once again available to us. So in this case, if we look at our PV equals nRT, once again, we have temperature, pressure, we're looking for volume, we have R. So in terms of the H2 and allow us to get there, we do need to figure out the mole. So that's really where the other piece of information comes into play, which is kind of the only thing that's not going to go into the gas law, which is our 5.65 grams of P4. In this case, we want to start with the balance equation, which we do have. We want to convert our P4 into moles, and we would go to the periodic table once again for P4 and do 4 times 3097 grams per mole. And that's going to get us 4 times 3097. Looks like 123.9. We're going to use as a conversion factor. So we're going to go 123.9 grams on the bottom per mole of P4. The grams will cancel, and that's really our second step here along our way. We're now into moles of P4, but as we can see over here, we do need H2 to get to. So that's where the stoichiometry is going to come into play. So we're going to look at our equation between, in this case, our 2 reactants. So remember, stoichiometry doesn't always mean you got to go across the arrow. You can stay on the same side of the arrow here, and that will get you 1 mole of P4 equals 6 moles of H2. So we're going to use that as our next step, which is really our third step in our sort of stoichiometry problem. We're going to get rid of the P4. So 1 mole P4 in the bottom, 6 moles of H2 up on top, and that's going to cancel. And that's really like our third step in our stoichiometry play. We got 5.65 times 6 divided by 123.9 And that's going to give us something like 0.273, maybe 4. Moles of H2. Any question on that part so far? So really, again, just a basic sort of stoichiometry problem up until this point. The difference really is in that sort of fourth step. Instead of using that molar mass like we have traditionally done, we're now going to go into the gas law and basically solve it. And in this case, in terms of units, once again, it is just our temperature that we do need to convert. And that's going to give us 300 Kelvin. So going into our PV equals nRT and solving for our volume, putting in our numbers, 0.274 moles of H2, our gas constant that we always have, our temperature 300 Kelvin, all divided by our pressure here, 1.25 atmospheres. Atmospheres cancel, Kelvin cancel, moles cancel, leaving us liters. And in this case, looks like we will end up with 5.39 liters of H2 in this case. Any questions on that one? This is not a yield, right? Because this is a reactant. So remember, yields can only be reactants. I'm sorry, only be products. But this is how much of that H2 you would need to throw in there with that many grams of phosphorus to generate this reaction and whatever you theoretically would get. Any questions on that one there? All right, let's take a look at one more here, maybe. All right, let's try this one here. This is pretty much like what we did last week, I think. Magnesium reacts with hydrochloric acid, produces some hydrogen gas. What is the volume of hydrogen gas produced at STP if we started with 5 grams of magnesium? Okay, let's take a look. So once again, we are looking for the volume of hydrogen gas. So we'll put that in our sort of our gas category at STP. So once again, a reminder that when it is STP, it actually is a temperature and pressure value. Temperature is what? 273. Pressure is 1 atmosphere, right? So when they do say STP, they are actually giving you a pressure and a temperature. Once again, we could kind of see our ideal gas law shaping up. So we got our gas constant there. And again, if we look at our PV equals nRT, we once again have temperature, gas constant, pressure, looking for volume. So once again, here we are looking for the moles of hydrogen gas to allow us to get there. That leaves one piece of information left, which is magnesium, which I guess I should have gave you perhaps that. I hope you found it. 431 there from the periodic table. So we'll start with balanced equation, which we have. We then will convert to moles. So we're going to take our 5 grams of magnesium, going to use the molar mass from the periodic table, which is 2431 grams per mole of magnesium. This once again will convert us into moles of magnesium, which is what we need because we are interested here in hydrogen. So that's going to be the stoichiometry part that's going to allow us to do that. And in this case, we have 1 mole of magnesium gives us 1 mole of hydrogen. Once again, here we could just continue on with the calculation, going opposites to cancel. So 1 mole of magnesium on the bottom, 1 mole of hydrogen up on top. Our moles of magnesium cancel, and that's sort of like our third step there in our calculation. Going to get us 5 basically divided by 2431. And get us 0.206 moles of hydrogen. Any questions up to there? At this point, we're good to go into our ideal gas law. So our PV equals nRT, solving for volume, nRT divided by P, 0.206. 0.08206 liters atmosphere Kelvin mole, and our 273 Kelvin divided by our 1 atmosphere here. Atmospheres will cancel, Kelvin will cancel, moles will cancel, leaves us liters that's left over. And that gets us 4.61, looks like 4.61 liters of H2. Since this is a product, this would be our theoretical yield in this case. Yeah. First off, any questions on that? Could I have solved this a different way? How else could I have solved this? Exactly. So since we are at STP conditions, this is a situation where we could have used the 1 mole is 22.414 liters, which means once we got our moles of our H2, we could have took it and a conversion. The moles will cancel and we would end up with the same answer. So you could have alternatively done that. Again, because this was in STP conditions, a reminder as well, as you can see, if you can't remember that or not sure you should use it, you could just go into the ideal gas law. They both will get you the same answer. Any questions on that there? All right. Why don't we try this one and see a little more involved one, see what you come up with. Calcium carbonate reacts with hydrochloric acid to produce carbon dioxide gas. If you take 35.3 grams of calcium carbonate and react it with 21.9 grams of HCl, how many liters of carbon dioxide gas would be produced at 745 millimeters of mercury and a temperature of 23? So I'm gonna give you some numbers here. 4008. Carbon 12.01. Hydrogen 1.008. Oxygen 16. That might be all you need. So follow the steps there, which in this case looks like we need an equation. Yes. So write the proper equation and balance it. Think about what's going on in that equation. That everybody has the equation, and I'll let you continue on. So remember that when we need to write the equation, we want to start with the proper formulas, right? So calcium carbonate, calcium is +2, carbonate is -2. Again, when we put that together, that's going to give us CaCO3. And we're going to react that with our hydrochloric acid, which obviously should be HCl. So what we got going on in this case is we have a double displacement reaction, right? Positive, and negative. So what happens in this case, right, is our 2 positive guys will switch partners. That's going to give me a calcium, which is a +2, and a chloride, which is -1. Remember, we want to put them together properly, which means we should end up with CaCl2. And that means the hydrogen, which is really +1, and our carbonate, which is -2, is going to come together to make a little carbonic acid. First off, any questions on that? Now, where did the CO2 come from? If you remember when we talked about types of reactions, this guy will actually go through a decomposition reaction, and that is where the CO2 is going to come from. This guy is going to break apart into H2O and our CO2 gas. So if you remember, this is one of those types of guys that will actually go through a decomposition reaction. So we actually have a double displacement reaction followed by a decomposition reaction that's going to generate that CO2. Any questions on that there? So cleaning it up and getting us to our proper sort of formula, calcium carbonate plus some hydrochloric acid, going to give us some calcium chloride and some water and a little CO2. And we now need to balance it, right? And it is not balanced, so putting a 2 right about there will get us balanced at this point. All right, back to the problem. Okay, so let's take a look. So once again here, we're looking for CO2, which again is going to be really a result of a decomposition reaction that's going to occur after the double displacement reaction. So we're looking for this volume. We again have a pressure that is 745 millimeters of mercury, and we got a temperature that is 23 degrees Celsius. Once again, we always have R. So if we think about, again, our ideal gas law here, we have our temperature, we have R, we're looking for volume, and we have pressure. So once again, in order to figure out the amount of CO2 we're going to produce in this case, we will need the moles of CO2. The only way we get the moles of CO2 is to use really the other pieces of information that's given to us in this problem and really stoichiometry to do so. So we have 35.3 grams of that guy, and we got 21.9 grams of this guy. This makes it what type of stoichiometry problem? Is it a basic stoichiometry problem or a limiting reagent problem? It is a limiting reagent problem because we do have the grams of both of our reactants, which means we can get to moles of both of them. So in this particular problem, we actually have to do our limiting reagent sort of calculation in addition as we're going through our stoichiometry calculations. So let's go through that. Once again, doesn't matter where you start, we want the equation, which we now have balanced. We want to take what they gave us and convert them into moles. So we'll take our calcium carbonate. We'll also take our 21.9 grams of HCl. We will go to the periodic table and calculate the molar mass of each of those. And once again, our molar mass is for HCl, it's going to be 3646 grams per mole of HCl. For our calcium carbonate from the periodic table, going to be 100.1 grams per mole of calcium carbonate. Again, just adding up all the parts, and that will get us those numbers. 35.3 divided by 100.1 gets us 0.3526 moles of calcium carbonate. We'll do the same thing here for our HCl. 0.6007 moles of HCl. These are, again, our starting amounts of each of these. So we do have to do that calculation to figure out which one's the limiting reagent. A reminder that you just need to do a calculation between the two reactants. So if I want to use up all my CaCO3, how much HCl is needed? So I'm just going to do that little calculation there, and that will tell me which one is the limiting reagent. So if I start with the moles of calcium carbonate using the mole to mole relationship from the equation, which is a 1:2 relationship between those two. For every 1 mole of calcium carbonate, I need to put in there 2 moles of HCl. The moles will cancel. That's going to get me 0.3526 times 2, which means I need something like 0.7052 moles of HCl is needed. I want to compare that to my starting amount. Do I have enough? I do not have enough of the HCl, which means that is my limiting reagent, right? So I do not have enough. Means that this guy is my limiting reagent. This one is my excess reagent. Remember, we have to do that to figure out how much product we're going to produce. So now that we know that that guy is our limiting reagent, that will determine how much product and how many moles. So 0.6007 moles of HCl. We now want to go to the equation and do the relationship between HCl and our CO2, which is a 1-to-2 relationship, 1 mole of CO2, 2 moles of HCl. So the 2 moles of HCl will go on the bottom, 1 mole of CO2 will go up on top, and that's going to give me 0.6007 divided by 2. That's a 0.3004 moles of CO2. Any questions on that part so far? Now that we have the moles of CO2, we need to do some conversions before we go into the gas law. So our temperature there needs to be 273 plus 23, 300 Kelvin. We also need to convert our pressure, 745 millimeters of mercury divided by our 760 to put it into atmospheres, which is what it needs to be in when it goes into the ideal gas law. So 745 divided by 760 going to give us 0.980 atmospheres. So now we have Kelvin, we have atmospheres, we got our moles. That's pretty much everything we need to finally finish this problem, which is RPV equals nRT. Going to solve for volume. And using our values there, which is 0.3004 moles. And really it should be about there. 0.08206 liters atmosphere Kelvin mole. Our temperature of 300 Kelvin, all divided by 0.98 atmospheres. Atmospheres cancel, Kelvin cancels, and moles cancel. Going to get us 0.300, which are 8206, 300, and 0.980. Going to get us about a 7.55 liters of CO2 would be produced in this case, and this would be a theoretical yield, as that is a product that was produced. So this one ties together a lot of chapters that we've been talking about. Yes, so putting formulas together correctly, writing proper equations, types of reactions, balancing equations, stoichiometry, and gas laws. Any questions on any parts of any of those things there? All right, should be professionals now. Perfect.